Hey, thanks everyone for coming out. I'm going to talk about the connection machine, which looks a little like this. Ooh, ah, it's pretty cool. And I find that the best Papers We Love talks are personal, like the best talks in general. And so I'm talking about this paper not because I do AI or hardware, but because it's a really beautiful, consistent model. And it failed. Which makes me concerned, is a beautiful model a white whale? And specifically, I'm doing a startup and I believe models matter. And so this makes me concerned, am I Ahab? And so I'd like to do something a little different in this talk as actually a murder mystery of who killed the connection machine. And I'd like to also make it personal in structure, that this is really the best version of a conversation with Dan Bentley. There's going to be lots of info that's at least 95% accurate. There are going to be digressions, some seemingly unrelated that thread back in, and some just because they're really cool. At least I think so. Going to try and synthesize a lot, and hopefully you come out of this with not just what's in the paper, but what you can take from it. There are going to be puns, fair warning. You can walk out now if that's not your thing. It's going to be pretty fast-paced, and because of the nature, it's more of a ride than a dialogue, so maybe a better image of Who Framed Roger Rabbit is this. Please keep your hands and arms inside the talk. So, our first character is Danny Hillis, who's a Ph.D. student at the MIT AI lab. And this this paper, The Connection Machine, is actually his thesis. There's another paper that was linked to for a while that's an earlier paper, and if you read that, I'm sorry, but I get to be less than 95% accurate because you didn't read it. But really, this thesis collects previous papers, and so it's also an opportunity to see how ideas form and morph over the course of a PhD to really come to this new whole. And I'd like to convince you that this is an impressive PhD thesis, because a good PhD thesis advances the state of the art in one area. But this actually advances it in three areas: image recognition, a new programming model, and parallel hardware, 65,000 cores. And I'd even like you to believe that this is an impressive, of-the-moment PhD thesis for 2015. Over on the right is a post from the Google Research blog where they got a computer to label that as 3 slices of pizza on a stovetop, which is pretty close. MapReduce is another programming model, and at the time, the biggest supercomputer had just under 65,000 cores per node. They had more nodes, but hey, he's a grad student, we can cut him a break on not being able to afford all the nodes. But as much as this seems of the moment in 2015, it was actually published in 1985, which gives me lots of thoughts. First, wow. Impressive is an understatement, but wait, maybe it's actually that he didn't build on 2015, wasn't of the moment, but actually was predicting 2015. And if that's the case, I think more people would know this. So what happened? Well, to investigate, we have to go back to the beginning of the paper or back to the future. Actually just back to the past, 1985. And he starts, I think, in this really clean, elegant way. And this follows up on the lightning talk. The title of the intro of the introduction chapter is "We Would Like to Make a Thinking Machine." And he uses this Picasso painting and says, hey, a human can look at this and in a second tell you it's humans on horseback near water. And that's good. That's what humans can do because brains have these neurons and they're all connected. But a computer can't do this. And a computer looks different than a brain. The computer, and this is following up again on what we just heard, the von Neumann architecture describes most computers we use. And the first one was the IAS machine, which I just think is so cool. the first digression. This is the first von Neumann computer, and that's Mr. von Neumann. It's called the IAS machine because it was built at the Institute for Advanced Studies, which is just a camp for dilettantes in Princeton, New Jersey. And the memory was actually 40 cathode ray tubes. They weren't used for display. They stored the memory. You can see them there. And you may think that you're pretty awesome because your case design has EL wire or your car has a V8. But I just want you to take home tonight that the first computer was a V40 of cathode ray tubes. And the von Neumann architecture, so the IS machine, the Turing machine, C is really just a portable assembly language for the von Neumann architecture. And the key idea is that it's easy to allocate memory. You just have some arbitrary amount of memory, whether it's RAM or tape or cathode ray tubes. Different programming languages pronounce it differently. Pointer, malloc, new, make, const. And I've given you enough context that now we can see the problem, which is that the CPU that's actually doing the thinking is only 3% of the silicon. So you paid for all the silicon that's sitting 97% idle. Drat. And if we color it, you can see, hey, I have a lot of blue and not much red. And the problem is actually this thin line. It's what's known as the von Neumann bottleneck. It's too thin. And Hillis says the bigger we build machines, the worse it gets. And this term, the von Neumann bottleneck, was coined by John Backus, who did a lot of parsing and then went to this big fancy dinner to receive the Turing Award. And he says, thanks for the highest honor in all of computer science. By the way, computing is doomed. And that was his Turing Award acceptance speech, was, can computing break free of the von Neumann bottleneck? And Hillis in section 1.3 says, hey, concurrency offers a solution. Let's mix processors with memory. So instead of this picture, let's have this, a lot of processing elements that mix the compute and the memory. And to figure out what we really need, he deduces the requirements from an algorithm that we'll get to. It's easy to just put more processors on a piece of silicon. You just add them in, you draw them in. That's my understanding of processor design. Probably. But how do we actually use them? How do we take advantage? And so he lays out two requirements. We need many processors. Yep, we've heard that, Danny. What's next? And we also need programmable connections. And so the connection machine architecture that he proposes has three dimensions. It has memory. Von Neumann architecture already had that. It adds processors and communication. So it's not just many processing elements, it's also having the connections between them. And you may notice that this looks a lot like his model of the brain. Not quite a coincidence. Section 2 of his paper is how to program a connection machine. And I don't know, if I built a 65,000 processor computer, I'm not sure that I'd waste any time before just bragging about it, but he does. And I think that really gets at what he wants you to hear, which is that everything he's done in silicon is really in service of this new model of computation. And what he says is, hey, a von Neumann machine, I said it was described by C. I'm not an AI person. He says it's defined by Lisp. And so he's going to define a connection machine with CM Lisp, which is some extensions to Lisp that add sectors, which are memory, alpha, which are processors, and beta, which are communication. So let's talk about CM Lisp, but I have to be honest about Lisp. There's this quote, a gentleman need not know Latin, but he should at least have forgotten it. And it's problematic about elitism and misogyny, but it was formative for me, and it's basically how I feel about Lisp. I've never programmed Lisp for more than 10 lines, but CM Lisp really uses the functionalness of Lisp. So let's go with it, but I have a little crib sheet. To do a function call, you put the parentheses on the outside of the function, and then you pass it arguments. I know. Assignment, there's this thing called setQ because Q, and so you can set the variable foo to 1 by saying setQ foo1, and sometimes you need single quotes. I'm trying. Just go with me. So vectors are basically just maps. They have a domain, keys, and range values, and an element is one key and one value. And so this is a vector saying, hey, the sky is blue, the grass is green, an apple's red. Cool. There are also some special kinds of vectors. A set maps every element to itself, and we can omit that duplication syntactically. Yay, sugar. A vector maps consecutive integers to values, and we have syntactic sugar for that too. And then there's a constant vector, which maps every key to one value, and we can omit the key. So this is saying, if you ask it for 3, it gives you 3. If you ask it for 0, it gives you 3. If you ask it for A, it gives you 3. If you ask it for sky, it's just a whole bunch of 3s. But vectors are more than maps, because each element is stored on a different processor, and the key is the address of the processor. And I think this shows the 3 elements of a good abstraction. It has to be easy to use, it has to be easy to implement and understand in a simple way. You could code this all up just with Lisp, but it also has to be possible to implement performantly. And that's what vectors do by storing each on a different processor. And so, great, I can put stuff into memory. La-di-da. Alpha is how I operate on it. So it turns an expression into a constant vector is the formal way of describing it. And then 2 sentences later, he gives us an informal way. Alpha means give me a zillion, where zillion is however many are needed. So I'm going to use an example that we're running a grocery store that has 2 branches in Manhattan and Brooklyn. So this is saying, hey, set Manhattan to be the count of items in Manhattan. There are 3 apples, 4 bananas, 1 ham. And Brooklyn has the same items but different numbers of them. If we want to add them together, we can say alpha plus, which takes the function plus and makes a zillion pluses. And then actually each plus happens on a different processor. So we've just added in parallel. Yay. It's actually a little harder to just add 1 to everything. Say we have some clerk who 0 indexes instead of 1 indexes, and we have to go clean up, because we need the plus to happen a zillion times, but we also need the 1 to happen a zillion times. And there's even notation to do this easily, where the dot just says, hey, I already have a zillion, don't re-zillionify, whatever, Manhattan. So, that's alpha. I have a lot of things in a lot of places. How do I get anything? I can't just go rooting around. And so beta reduction, this is exactly what was on the previous slide. If I want to beta plus Manhattan, that just takes everything in the values and reduces them using plus. So it adds them and it gives me the count of all the items. Keeping with the 80s theme, I can also beta max Manhattan, and that gets me the number of values in the largest bucket. I can mix beta and alpha, so I can add 1 to everything before I beta it. And each alpha happens on a different processor. Where does beta happen? And so this is beta reduction. It turns out there's actually general beta, where it takes an optional 3rd argument, and it does general communication, which, all right, let's do this. If I say beta f data addresses, it means route data to addresses and combine each key with f. So pictures are good. This is just what we've talked about. Great. So if I want to say beta, categories is new. Apples are produce, bananas are produce, hams are meat, welcome to a grocery store. And so if I want to say beta plus Manhattan categories, all right, I take Manhattan, I take categories, I send everything from Manhattan to categories, and then I send them to the destination that's in the values of categories. And apples and bananas go to the same place, so I'm going to combine them with plus. There's only one meat item, and so I get a result that's produce 7, meat 1. All right, no one is visibly upset, so we're going to keep going. And the example he uses, and this is the example algorithm from which he deduced the requirements, is find the shortest path from A to B in graph G. I'm going to do pseudocode on the left and then CM Lisp code on the right. We're going to start, just label all vertices with infinity. Then say, hey, A, where we're starting is 0. And we're going to label every vertex that's not A with the minimum of its neighbors plus 1. It takes one more hop to get to. We're just going to repeat until B is finite, and then terminate, and hey, the answer is B. So defun is how you say the rest of this isn't going to be very fun. No, it's how you define a function. And we're going to just, in parallel, set the label of everything to infinity. So boom, one step. Then we're going to set the label of A to 0, and then we're going to loop until it's less than infinity, and we're going to set in parallel the label for everything in G except A to 1 plus, which I guess is a function, fun times. We're going to reduce to get the minimum of everything that's a neighbor according to the graph connections G. Then we're going to tell Lisp that we're pretty much done with a bunch of parentheses, closing them, and then we're just going to return the label of B. All right, take a breath, take a sip, you've earned it. We've just done parallel programming so that this only takes as many steps, as many iterations through the loop as the path is, not the number of nodes times the average number of connections. Ta-da. Yeah. So that's how you program it. But what are you actually programming? So section 3 is cool because it's design considerations. Here's all of the questions you could ask given this programming model. How do we want to build this computer? How big is each processor? You know, real math takes 64 bits. 32 bits are coming into prominence. 16-bit, 8-bit is really what's on the desktop. And because he's just thinking of, hey, it's all just silicon, we're all just putting it in the mix, each time we double the number of bits per processor, we have the number of processors. And up till now, every computer is really focused on getting the biggest, beefiest processor. Maybe we should optimize the number of processors instead. And so section 3 is just all of these questions. Section 4 is actually what they built. And they built 65,536 processors, 2 to the 16th. And each processor is 1 bit wide, which is the minimum you need to be a processor. And each processor they pair with 4,096 bits of memory. So it's right there next to the memory, able to do whatever you want locally, yay alpha. And the network topology, okay, yeah, this is going to take a sec. I promise I can't promise. It'll probably be worth it. If you just have one processor, you have a point, you don't need any you don't need any network. If you have 2 processors, you have a line. Cool, they're all connected. If you have 4 processors, there's a square, and there's actually some missing connections here. To get across a diagonal, you can't just send it to the processor it wants to go to. You have to send it, and it has to be sent on. If you have a cube, oh, the diagonal is now 3 long. The worst case is 3. If you have a hypercube, 4 dimensions. And so to see what the connection machine actually does, just imagine this in 12 dimensions. And that's what it does. And a hypercube is good because each node only has log n connections, not n minus 1. And the worst case is only log n. That's not so big. But it's not so great because you have to deal with traffic and buffering. And it just can't scale infinitely because each time you double it, it's only log n, but log n adds up. And he's imagining connection machines with millions of processors. I hope this isn't that last 5% of accuracy. A lot of the work to actually make the connection machine happen is in the communication. Section 5, data structures for the connection machine. What would it be like if allocating a processor were as easy as allocating memory? And the answer is pretty cool. There's a follow-up paper, Data Parallel Algorithms by Hillis and Steele, and in it they say, hey, adding numbers that's O of n on a von Neumann machine is O of log n. Okay, yeah, that's pretty cool. You just add them up in a tree and you send them to like neighbors and yeah, cool. Matching a regular expression, O of n, but you can't do better than O of n because like to match a regular expression you have to go through, right? It's really sequential. Actually also O of log n, which I just think is a mind-blowing result, and yeah, you should go read the paper and then get mad at it and then come back to it and make up and realize that, wow, yeah. So, the connection machine. This slide should probably be titled Thinking Machines Corporation. So Thinking Machines is the company that Hillis founded to actually build and sell the connection machine. And it just had amazing talent. To give you an idea, one of their interns was Richard Feynman, post-Nobel Prize. It was the third ever .com domain, think.com, and it's the corpse, the body in this murder mystery. It died in 1995. And so now we need to go to our lineup. Who are our suspects? So our first suspect, mugshot, George H.W. Bush. So what's the evidence? What's the case here? So DARPA subsidized supercomputer purchases to the tune that it was actually 20% of Thinking Machines' lifetime revenue. Then the Cold War ended and they rethought and they changed it and they pulled that funding. And so, hey, this just coddled the company. They didn't actually respond to market pressures. They were just, thinking thoughts. But, yeah, the sweetheart deals, the Thinking Machine got more subsidies than other supercomputer manufacturers. That's not great. But this is what research and VC are for. Thinking Machines was swinging for the fences of what if we actually change computation. So George H.W. Bush is innocent. And after beta tests, I had to add of this to the presentation. All right, this is just random clip art for product management. And this is kind of related to the last one. There's this product management proverb, sell pain relievers, not vitamins, which means focus on solving real user problems, not the virtues. And this criticism of Thinking Machines goes that they were built by AI researchers for AI researchers. And if they hadn't have been coddled, including by George H.W. Bush and DARPA, they would have focused on existing high-performance computing users instead of just going off on their thought bubbles. And this was really popular, right after they died. Like, look, there are all these competitors, and all the other competitors focused on existing supercomputer users, and they died. So that's not really a convincing case, right? Because it doesn't really matter. They all died. AI winter, supercomputer winter, that's maybe a term. It is now. So product management is innocent. Who's this other unassuming white guy? Gordon Moore. And the evidence here is more circumstantial. I'm sorry, can we get that a bit more 80s-ified? Okay. So in the 80s, there was this line of thinking. So here's the Intel 4004, the first microprocessor. And over on the bottom left is the ALU, the arithmetic and logic unit. And it's a pretty small fraction of the processor, but it's the only part that's actually computing. And so the thinking goes, let's make a simpler chip that removes the overhead, everything else, and just focuses on the ALU. And this is called RISC, Reduced Instruction Set Computing. How'd that go? So, okay, at time zero, you have this great idea of a better architecture. Then you have to build the computer. Then it turns out that's hard, so you have to debug it. And in that time, Intel has made a chip that's nearly as good, but you're still better. All right, we can work with that. And then your customers have to actually choose the computer and port and optimize their software. by which point, okay, well, that's less good. And so Moore's law, which says that computers get better at double every 18 months, just beats whatever brilliancy. Even if you're 10x better, which you weren't, you only have 5 years to get it into the hands and actually producing before Moore's law beats you. And so Intel beat RISC in desktop, and we can talk about all the caveats afterwards. And it's also, yeah, this is just cool. So back in the day, Dell would mail you a computer directly, whereas Compaq and HP and Packard Bell and other companies you haven't really heard of sold through Staples. And Moore's law, the rule of 72 is about compound interest doubling. Computers get better at 1% a week. So each week that you're in a supply chain lowers your profit margin by 1%. And Staples is built for pens. And pens don't lose value at 1% a week. So goodbye, everyone except Dell. And now they just sell through Staples. Good for them. So Moore's law means that Intel will beat von Neumann computers. But the connection machine breaks free from the von Neumann bottleneck. So Gordon Moore is a serial killer of computers, but in this case, he's innocent. All right, so this is the Athens mob. And one way of going is that were programmers put off by all of the alphas and betas? Did they even have the keys on the keyboard? Or another way of putting this is, was the connection machine killed by a couple of Greek characters? Sorry. Your existing code just didn't work on the connection machine. And here's a quote from Tony Hoare. I don't know what the language of the year 2000 will look like, but I know it will be called Fortran. And yeah, it's still called Fortran. So actually the CM Lisp I showed you never shipped. They made Star Lisp and Star C that were way more conventional. But fundamentally, a new architecture requires a new paradigm. And the eventual winner also had a new model. So innocent. And I just said the eventual winner. And I just want to assure you, this isn't a dead-end story. Parallel computing matters today. It's everywhere. But it's not parallel supercomputing. And so we need to take a break. These aren't suspects. Don't cast aspersions on deep learning and how it matters. So deep learning is a lot like a slide we've seen a few times. In the 50s, there were neural nets, and in the 80s and 90s, they figured out if you add more layers, you get really impressive results that you just can't actually do anything with because you need so much data and so much computation. And so to set the stage, this is also in that 5% of mostly accurate. Every subfield of AI, image recognition, speech to text, text to speech, has an annual competition where you measure the error rate. And hey, if you can get 2% in a year, you've made it, you can coast. And the competitors are like industry sends 30 PhDs who have dedicated their careers to these. Academia sends a professor and their postdocs and grad students. And so in 2012 at an image recognition competition, in walks a grad student. And he was working with a professor and a postdoc, but it was largely him. And he achieves a 10% improvement overnight. He's 10% better than second place. It's called AlexNet. His name is Alex. Not that surprising. And this has happened in pretty much every field of AI. And so just to give you examples, I think this is even more impressive than recognizing what's in a photo. This is called style transfer. You give it a photo and then another photo, and it redraws the first photo in the style of the second photo. So that's Mona Lisa as rendered by Picasso. AlphaGo uses deep learning. And what sparked the deep learning revolution was porting deep learning to GPUs. And based on everything I've told you in this talk, your next question should be, what the heck's a GPU, Dan? It's the graphics processing unit. The 3D card, they started in the 90s. And they have parallel computation. So they look like this, which also resembles slides we've seen. And at the beginning, they were real limited. They weren't programmable. You couldn't even do floating point. But then in 2007, CUDA lets you start writing programs in C, and pretty much all deep learning since uses GPUs. And takeaway, this is true. It's not directly related to this paper, but if you remember anything, this is a pretty good one to squirrel away. AI was delivered by largely teenage, largely males, paying to frag fancier looking zombies. GPUs are really what did it. And so our next suspect is the wrong horse, which is to say, did thinking machines hitch the right wagon to the wrong horse? They had the right idea, parallel computation, so the story goes, but they sold to universities and governmental agencies with 3-letter acronyms. But disposable income is way bigger than research budgets. Should they have gone consumer first and then done the science later like GPUs did? And, this paper considers other architectures, including GPUs, and says, no, they can't do AI. They're not suitable because they lack communication. So, it's not quite innocent. It's closer, but the trick to do AI on GPUs was unknown for 20 years. So we're going to say not guilty. And the trick to do deep learning on GPUs is this paper says, hey, it's so easy to allocate processors. We're going to have one processor per neuron, per whatever we're simulating. But deep learning actually puts many neurons onto one processor. And this works because it turns out sparsely connected neurons, sparsely connected neural nets work really well. So if you have fast local communication and just limited remote communication, you're fine, you're good. And so sending data between same processor neurons on a GPU is a matrix multiply. And a matrix multiply is the basis of 3D graphics. So GPUs are really good at it. Another digression. Well, here you are. The connection machine is named after the communication. That connection is so important. But what replaced it is also actually named after how it does communication. A vector is a 1D array, a matrix is a 2D array, and you call an n-dimensional array a tensor. And TensorFlow is what you use to do deep learning. Again, I don't do AI, but none of you are visibly upset at me. So we're going to say that's in the 95% of accurate. All right, product management. And you're thinking, hey, we already talked about product management, but this is a different kind of product management. The connection machine added 2 concepts to the von Neumann architecture, processors and communication. In Occam's razor, we normally say the simplest solution is the best, but a more literal translation is don't multiply unnecessarily. And by adding 2, connection machine multiplied the risk of adding processors and adding communication, which to me sure makes it sound like they did a bad job of managing the product. Which is, I assure you, the worst pun in this talk. It's all uphill from here. So I'm going to go out and say that this general beta isn't a good abstraction. It's not particularly easy to use or to understand and implement. It's really hard to implement performantly. And part of the art of abstraction is knowing when not to generalize. So I'm going to enter into evidence another parallel computation model, MapReduce. And map is a lot like alpha, and reduce is a lot like beta reduce, and general beta is a lot like shuffle. Wait, it's called MapReduce, not MapReduce shuffle. What's shuffle? It's not even mentioned in the paper. And it's the magic that makes MapReduce fast. And they couldn't abstract it, so they just left it as an implementation detail. And so now I think we've reduced this question to, could Hillis have reasonably known at the time that general beta was harder than it was necessary? And I'm going to prove to you I'm not a lawyer by misusing the term mens rea, which means mind of the thing, to show there's this 1981 paper, New Computer Architectures and Their Relationship to Physics, or Why Computer Science is No Good. And it talks about the locality of action in physics. You don't have to consider Jovian moons when calculating the orbit of Mercury. If you're trying to send people to the moon in Apollo, you obviously aren't going to get there if you still believe in geocentrism and that everything's just, spheres on epicycles on stacks. And there's Newtonian mechanics. But, just 50 years ago, there's relativity. I put Einstein in case you didn't know who came up with relativity. And it does, so just imagine this person rushing in, hey, we need to throw out all of this physics we know. Let's use relativity to calculate it. Slide rules bursting into flame from the sheer number of computations. And it turns out it does affect the orbit of the moon by 1.3 centimeters. So it's just not actually meaningful. And I think there's a case to be made that relativity is a bridge too far for Apollo, the same way that general communication is for the connection machine. So maybe, they just got stuck on the means on building this thing instead of the ends. Or actually, look, for AI, we know you don't need general communication, but databases don't have physical analogs. Maybe they need general beta. And so maybe actually it was that the connection machine was just so focused on, even though it was by AI researchers, being for all of CS. And I've made you sit here and you've been very polite for a long time. Who wrote this 1981 paper? Could Danny Hillis have read it? And the answer is Danny Hillis. It's actually section 7 of his thesis, one of the papers he stapled together to turn in. And so, thank you to everyone at Thinking Machines. It's easy for me to get up here and opine on what obviously must have been, but it seems like it was real exciting to actually be trying and building. Thanks to PapersWeLove and the organizers for putting together such a great event. 2 Sigma for hosting, and I know a fair number of people at 2 Sigma, and to an individual, they're all really brilliant and care about this kind of thing. Thank you to all of the beta testers who saw much worse versions of this talk, and thanks to you, you've been a great audience, and even if you weren't, it was already in the slides, so you were going to get mentioned.
Thank you so much. I think we have time for some questions. So we have people with mics, so wait for someone to come to you. If you have a question, raise your hand. Nice, and there's one in the back. Darren, I think you can... let the mic come to you real quick. We want to get it for the video.
My gut instinct is to believe you on the theory of relativity and the actual effect of it in the distance of going to the moon being like a centimeter or whatever. I was just wondering if anybody else wanted to weigh in on that, because I'm not a physicist.
I checked Stack Overflow, so my understanding is that that's
the ultimate answer for all programming questions. They would know too, probably. Yeah, Wolfram Alpha might also know. Other questions? Billy? No, everyone in back again.
So at Google, we'd probably ask, was there a postmortem? How did Danny forget about his own paper showing general beta was unnecessary, or what happened?
Oh, that's a great question. One answer is that yes, you just saw it, and another answer is that you have cleverly stumbled upon the appendix slide of homework questions that you can go investigate and learn from, because I had a great time researching and learning and thinking about this, and I hope that you can learn some things and also be curious about others.
That was an excellent non-answer.
Yes.
I'll be right in front here.
So my question was if you knew about any resurgences maybe in hardware to build something based off the connection machine architecture that's not been discretized like a GPU. Maybe if there's anything like that.
Oh, so yeah, there's all of this awesome research on GPUs, general purpose GPUs, and so like Intel Larrabee is an attempt to bring that. A professor at Stanford had a project, but now he's the chief scientist at NVIDIA. And so I think there's all these people who think, hey, stream processing is more useful. Let's do it not just for graphics, but also for routing, for DNS lookups. Where else can we, for database queries, if we can have all these things sitting in memory, let's set it there. And yeah, so GPUs is the term to perform an internet search using the Google brand search engine and spiral out from.
So going from a Lisp dialect to new silicon is kind of a major leap. Was Danny Hillis like a hardware guy from the start, or did he just kind of know where to find hardware guys and how much to pay them?
I think at the time, it wasn't always clear that your CPU should be one chip. And there was a culture at MIT of building your own computer. And so Lisp machines were another kind of workstation that was coming out. And so there was the integrated circuit, then large-scale integration, then VLSI, very large-scale integration. And so the connection machine was actually a whole bunch of chips wired together. And so it was still, you could change the computer you were working on physically.
So I think you were talking about selling pain relievers. Did they have a poster child problem they were trying to solve? Because if they were doing something that they thought, oh, let's do this general problem, they would run into this problem right off. They'd say, we have to shuffle this memory around so much. That's going to be most of our problem. I mean, that's the problem with GPUs as well. But if you're doing matrix multiplications in a very highly local way, GPUs are good. Did they have a problem where they said, this is going to totally crack that egg?
I think they'd say a lot of problems have this. And what you're doing with supercomputing, we believe the connection machine can be better at. And so I'm not entirely sure of what their brochure said on page 1. And I'd refer you to some of the Thinking Machine employees in the audience afterwards for what the tactic was which year. But I think it was, hey, this is better, and it's going to apply to a lot of things. Let's figure out where and get there. But the name Thinking Machines, clearly general AI. I think I heard the phrase, we'd like to create a computer that thanks us for creating it, was still the guiding raison d'etre.
I might have missed at the beginning. Are your slides and/or speaker notes going to be posted anywhere? By
Yes,
chance?
if you go to my Twitter, which is at the bottom right slide of every slide, including this one, I tweeted them in a tweet before talking.
We'll add that when the video goes up as well. We'll add a link to them. You got one? Yeah.
Yeah, maybe I have a little naive question. It's not going to be a statement. In many different applications, you'll find a niche where a computer lives long after it should be dead. Did the connection machine have any great wins that you know of? Like anywhere that it embedded itself that took a long time to get it out?
I believe there was a model that was working at the NSA for far longer than you would expect a computer to continue to operate given Moore's law. And if you think about the kinds of problems that involve streams of data and trying to do a bunch of things in parallel on them, you can imagine that that is one such. Also, it has a cameo in Jurassic Park, the movie, which lives on in my memory in childhood, if not yours. So,
Where was the picture from the first slide from? Is there one of these in a computing museum somewhere? I seem to recall.
oh yeah,
Okay.
it was at the Met. There was an exhibit on on computers that are cool modern art, and this was that as well.